Ladies and gentlemen, let's continue with radiation. Today we're specifically going to do solar radiation, paragraph 12.6 out of the textbook of Cengel and Ghajar, which is atmospheric and solar radiation. Right, atmospheric and solar radiation. Just a few interesting facts about the sun. We know that the sun is our primary energy source. It's our primary energy source. And the energy that we're getting from the sun is called solar energy. So the energy that we get from the sun is called solar energy. We get it, as we've discussed, in electromagnetic waves. However, after interaction with the atmosphere, which is not so simple, but we're going to discuss it just now. The sun is a nearly spherical body. Its diameter we're going to use that later on in the calculation, is approximately 1.39 multiplied by 10 to the 9 meters. Excuse me. Or then 1.39 million kilometers, so it is very, very big. Its mass is approximately 2 times 10 to the 30 kilograms. Okay. And the mean distance from the sun, from the surface of the sun to the outer surface of the earth is approximately 1.5 multiplied by 10 to the 11 meters. And the energy which is being emitted from the sun is approximately 3.8 multiplied by 10 to the 26 watts. Okay, it's a big number, but sometimes important that we get a little bit of perspective on what it really means. So let's compare it typically with a typical power station. Okay, we know that one of our biggest power stations at the moment that has been generated, power stations, consists out of 6 turbines which can each produce 800 megawatts. Okay. 6 units which can produce each approximately 800 megawatts, which means it is 4.8 gigawatts of electricity which is being generated by a big power station. Right, so how many power stations does the sun represent? Okay, it's very easy. That divided by that. Okay, that is the energy that is being emitted. That is typically the energy that is produced in a power station. And if you do the calculation, the number of power stations that would produce the same energy as the sun would be 35 million. Okay, 35 million power stations is the equivalent of the energy being emitted by the sun. Right, now, if this is now the sun with all its radiation, sun, it is emitting, as we've said, 3.8 multiplied by 10 to the 26 watts, and it radiates it in all directions. Now the Earth, if that is the Earth, and obviously it is not to scale, okay, it is not to scale, the Earth would obviously not receive all the radiation being radiated in those directions. It would only receive a small amount of the radiation emitted by the sun. So what the Earth would absorb is approximately 1.7 multiplied by 10 to the 17 watts. So that is what the Earth will get. And as you know, it is just one side of the Earth which typically is exposed to the solar radiation per day. The other side would emit radiation to the atmosphere again. Okay, so what we are receiving is sufficient to keep the Earth warm and to sustain life. The sun itself is actually a process of fusion which occurs. It means that you get hydrogen plus hydrogen, which fuses hydrogen atom plus another one which forms hydrogen. Okay? And the energy that is being released is fusion, which is actually a nuclear reaction. So the sun is actually a nuclear reactor. Okay. The sun is actually a nuclear reactor. Okay. In the core of the sun, in the center, the temperature is approximately 40 million Kelvin. Okay, in the center, temperature is approximately 40 million Kelvin, while on the surface we know, we've already discussed it, temperature of the sun on the surface is approximately 5,800 Kelvin. Right, now if we look at the Earth, in terms of how we would typically receive radiation, then the Earth will have an atmosphere, and I'm going to say a little bit about the atmosphere a little bit later. Now the atmosphere has a height of about 30 kilometers. So the atmosphere of the Earth is about 30 kilometers in height. Okay. Now, if we now look at the sun, that is the sun, and if we look at the radiation coming from the sun, and we would put 1 square meter of surface on the outside of the atmosphere, then depending on what time it is during the day, it can get the sun radiations at an angle, or if it's at 12 o'clock, it would be at perfect at 90 degrees. Okay. So that angle is called theta. Okay. And obviously the radiation is like that. Okay. Now, if we would measure the radiation at 90 degrees, okay, then that radiation is called the GS. Okay. It is the total solar irradiation. Total solar irradiation. And its value would be equal to 1,373 watts per square meter. 1,373 watts per square meter. Thus, if I would measure here on the outside, would I always get a radiation of 1,373? The answer is no, only at 12 o'clock. Okay, only at 12 o'clock. Because then the cos of the theta would be 1. Okay, and the radiation would be perfect. So if the sun is now there, if it comes into this direction, and on that surface it is 1,373, if we put the same surface just outside the atmosphere, then the maximum it can get is 1,373. But that would only be at 12 o'clock. So it will always be less than 1,373. Do you agree? Okay. So if we would plot a curve of the radiation that we would measure on that surface there, and this surface here, or that radiation, we call G0. Okay. And G0 would be equal to Gs multiplied by the cos of theta. Okay, so if theta is equal to 0, theta is equal to 0, then G0 would be equal to Gs, because if theta is 0, then the cos of 0 is equal to 1. Okay? Then, as the sun would move away, the cos of 10 degrees, 20, etc., up to the cos of 90 degrees, it would be 0. So in general, if we would look at G0 as a function of time, and this is at 12 o'clock. So at 12 o'clock, we will get 1,393, or 73. And we will get something like that. So this is when the sun rises, and that is when the sun sets. When the sun rises, then it would be there at an angle of 90 degrees, almost 90 degrees, and then a little bit less, and then the angle effect is being taken into consideration. Follow that? Okay. Now, if we would go and do an energy balance in terms of radiation, now that we know how far the Earth is from the sun, we know how much energy is being radiated by the sun, we can actually calculate the temperature of the sun if we do this measurement of 1,373. So let's just go and check it in terms of an energy balance. Okay. So the sketch that we're going to use is, this is the sun with a radius r, okay, and it emits radiation in all directions. So the radiation of the sun, if we assume it is a black body, is equal to sigma temperature of the sun to the fourth. Okay. While here far away is the Earth. There's the Earth, okay. And this is typically the distance L between the sun and the Earth. Now this 30 kilometers, adding or subtracting, adding it or taking it away is not going to influence the result at all. So you can go and check it, because the distance is just so far. Okay. But remember, here we actually take the measurement of Gs. Okay, of Gs, which is equal to 1,373 watts per square meter. Okay. And if we look at an energy balance now, if we look at the sun as a sphere, okay, okay. So, look, okay, in terms of this distance here, look at all the heat transfer on that surface there. Now remember, it's not a two-dimensional surface, it is a three-dimensional one. So we have to look at the outside surface area of a sphere. Okay, so if we look at the outside surface of a sphere, it is equal to pi multiplied by 2L. Okay, remember, because this is just the radius, and we want to look at the diameter, 2L to the square of that multiplied by Gs. So that is all the radiation passing the surface there. We take a sphere around the sun, pi multiplied by the diameter is 2L, square Gs we've measured it, and that must be equal to what is being radiated by the sun. And that is equal to pi multiplied by the diameter of the sun. the diameter of the Sun square, multiplied by the Stefan-Boltzmann's constant, multiplied by the temperature of the Sun to the fourth. Right. So it is pi multiplied by 2 times L is the distance, this mean distance typically of 1.5 multiplied by 10 to the L, 10 to the 11 square. Okay, so that is the diameter. The diameter is 2 times 1.5 multiplied by 10 to the 11. That we've measured is 1373. Is equal to pi multiplied by the diameter of the Sun. The diameter of the Sun is 1.39 multiplied by 10 to the 9 meters square, multiplied by the Stefan-Boltzmann constant, 5.7 multiplied by 10 to the minus 8, multiplied by the temperature of the Sun to the fourth. And if you then solve it, you get that the temperature of the Sun is equal to 5,780 Kelvin. Okay. Does that make sense? Okay. Now if we would now go and take measurements outside the atmosphere and inside the atmosphere, we would like to see how these measurements look like, isn't it? Okay. Now, we have to remember that in terms of the spectral irradiation, it's a function of the wavelength. Okay, it's a function of the wavelength. And if we have a black body, remember a body at 5,780 Kelvin, you remember in terms of taking the wavelength and the temperature into consideration, we can calculate the energy that is being emitted. Okay, so that is how it should look like for 5,780 Kelvin. My curve is not really to scale. Actually, this optimum is a little bit to the left, and then it stretches out to the right. Okay. Now, if we let me see if I can get that right. So this is typically how the measurements look like on the outside of the atmosphere. Okay, Marlies, you can go to the laptop. Okay. Okay, what do we see? Okay, you have to be very careful when looking at this graph because there's a lot of information in the graph. Okay, the dotted line is for temperature of 5,780, so that is how it should look like. Okay, if you go and take the measurements at the different wavelengths, then this solid line here is the experimental line. Okay. You can see it's not perfect, but it's there. Okay? Okay. Something else that many people miss is in this same graph is the information of what also. What else? What other information do you see there? Except now for the gases. We will get to the gases a little bit now, a little bit later. But the Earth's surface is also given there. Do you see it? That one here, if you follow the hand, is for the surface of the Earth. You see? And what is the peak there approximately? The peak is almost about 1,200 watts per square meter. Okay. So it cannot be 1,373. We will get to that later. Okay. But here on the Earth, on the surface of the Earth, typically about 1,200 as a maximum. We will discuss it just now in detail. Okay, you see it? Okay. So take a good look at that graph. It's a very small graph there in your textbook, but it's a very important one. Okay, now The atmosphere causes a lot of attenuation. Okay, there are in the atmosphere, there's oxygen molecules, there's CO2, there's dust, pollution, etc. And in that atmosphere, we have to remember that if we look at this thick atmosphere of 30 kilometers, 30 kilometers, excuse me, that is where you'll get oxygen, ozone, remember, water, CO2, dust, smoke, water, vapor, etc. Everything is there in the atmosphere. And the 30 kilometers is a distance which is arbitrarily defined, just like the boundary layer thickness, as 99% of the height in which you'll get all these things. So 99% of the height, that is in which you'll get all those particles. So what now happens is here on the inside of the atmosphere, you remember that we've looked at a medium like this, and we said if you have a medium with radiation, incoming radiation, then a part of it would go right through, a part will be absorbed, and a part will reflect. Okay. In the previous lecture. Okay. The part that transmits right through would be equal to tau multiplied by G. The part that is being absorbed is alpha multiplied by G, and the part which is being reflected is equal to rho multiplied by G. Now this medium, very importantly, it is not always something like that is solid or glass or anything like that. A gas does the same. Okay. So a gas, any of these gases, a part of the radiation will be absorbed, a part would go right through, and a part would be reflected. Okay. Now, in general, the alpha is very small. Okay. So little is absorbed. Okay. But many of it is reflected, and most of it would actually go right through. So the fact that you have all these molecules and gases in the atmosphere actually now causes that here in the atmosphere you have lots of reflection. Okay. And the result is typically that here on the surface of the Earth, the average is about 950 watts per square meters. Okay. The average that would get through is 950 square meters. Now, let's look at typically, if I can open this. Now, the average of 950 is the world average. Okay. Now, if you look on this map, typically, unfortunately, the map doesn't become very clear as it is being enlarged. There are places on Earth where this radiation is much higher than other places. Okay. And here you can see typically with a very, very red areas here in South Africa, there in Brazil and in Australia, typically in the southern hemisphere. But that would be in our summer, of course. Okay. Okay, so if it is our summer here, then it is winter there, and then those areas there in North Africa, which are also high, would then be low. So obviously always the opposite. But you can see there's the equator, typically here in the center, and the sun would move down to summer, and then in winter it would go that way. So on this horizontal, if I can get this thing to move, as the sun moves in this direction, in our winter, in their summer, then they would get very high levels there of solar radiation, while in summer it would be for us here, and in South Africa, typically in the Northern Cape, we will get the highest values. Maybe this map might have a better resolution. Let me see if I can try this one. Okay. Right, I think it's a little bit better resolution, and there you can see all the areas with very, very high solar radiation. I see there in the squares typically are all the areas. I see there's nothing here in South Africa, but there should actually be another one there, because the area in the Northern Cape is among the highest in the world. Very, very high. Okay. Right. Now, in terms of how to quantify this, in terms of the G0, the GS, etc., what we're going to do is, or what we do is, we would say the G of solar, okay, which is the solar radiation incident on the Earth, on the ground. Okay. Okay, so incident on the Earth, on the ground, we would write it as GD multiplied by the cos of theta plus G small d. Okay. Okay. Now this one is the direct solar radiation. The direct solar radiation, and this one is called the diffuse solar radiation. Okay. So what we do is we say, well, let's make things a little bit simpler. We say, well, this is the sun, and here is the Earth. Okay. Okay, now the Earth is not always flat. Let me draw it a little bit like that. Or maybe, no, the other way around is maybe better. Okay, something like that. And we are interested in the solar radiation 1 square meters on the ground. Okay. So the radiation would firstly consist of the direct radiation. Okay, the direct. And here's the clouds. Okay. So this is called the diffuse radiation. Now, although I've drawn a cloud there might be not clouds at all. It is just the atmosphere. Okay. The effect that I've described in the atmosphere of all the different gases which reflects radiation, some absorb, some would let it through, and this total chain reaction that occurs would cause this diffuse radiation. So it would depend also from day to day on the weather. I mean, if there's clouds or rain or whatever, then it would influence this component of the diffuse radiation. And then the third component would be reflection. Okay, so the reflection, like that. So those are the three components of radiation that we can get. Yep.
So for instance, the value of the diffuse, will it increase on a more cloudy day, or what's the ratio? Will it increase?
It would typically increase, but then this one would typically be lower. So it depends. It's a little bit, it is complicated, and I'm going to show you graphs of it just now, if you give me a second. Okay. So on the roof of the Engineering 1 building, we have a project with a few universities. Yeah, if I can get this thing to move. I don't know why it's giving me so much problems. Okay. And every day I get a report on typically what the radiation levels was right through the day. Let's see if I can get it. Oh, there it is, daily report. That is what its name is. And that is how it looks like. So that's on the roof of engineering, on the Engineering 1 building. It's a project with a German company, GIZ, and then us, together with Stellenbosch University and a few other universities, have a few of these weather stations all over the country and also all over the world. So what it does is every minute it logs the radiation, also the temperature, wind, etc. Now, I don't think you can see it very clearly, but this is for the past. I've received this yesterday, so it was for the 3 days before that. Okay. Now, if you look very closely, you will see that there are actually 4 lines. There's a blue line, a red line, a yellow line, and a green line. You can't see it very clearly, but I'm going to help you with it just now. Those dots there are actually, somebody has to go and clean the lenses every second or third day. And that is actually when there was somebody there that actually cleaned it. And maybe on that day there was maybe a big bird or something also like that picked up that. Okay. Okay, but here we also log the temperatures and the wind speed and everything. Okay, so just before the lecture, I've asked Marlies to go and draw me a better map with thicker lines. And let me see if I can show that to you. Oh, there it is, right. Okay, so Marlies, read what she did some curve fits through it, and you'll see then the 4 different lines for the 3 different days. Okay, so here you can typically see at what time in the morning, approximately 6 o'clock, until about 6 o'clock at night, something happens. Okay, then in between, obviously there's nothing. But look at the 4 different lines: GHI average, DHI average, DNI average, and DNI calculated average. So what are those 4 different lines? All right. So the lines are the following. The DNI is the direct one. If you would now, I'm going to draw you a sketch. For 3 different, for the morning. So here it is in the morning at 6 o'clock. Then it is at midday at 12 o'clock. So the sun is now there. And this is now at 1800 hours. And the sun is setting typically there. So there are the 3 different positions of the sun. Okay. Now consider you having a solar collector on the roof of a house. And let's make it as a roof which is like that. Okay, so there's your solar collector. Okay, so 6 o'clock in the morning, it is also going to be mounted like that. And 6 o'clock at night, it is also going to be mounted like that. Okay, but you're also going to do an experiment. You're going to take a similar collector and you're going to stand here and you're going to orientate the solar collector so that it is perfectly aligned to the sun, like that. Okay, so here you're standing there and you're keeping the solar collector like that. Okay, okay. So you can see that this solar collector is going to, the sun is just setting and you're keeping it like that. The radiation, the angle is going to be the angle is going to be 0 degrees. Okay, so in this equation of us, if this is equal to 0, we've also written it down somewhere else. Here, yeah. So if that is equal to 0, then that radiation and that radiation would be the same. So that is called the DNI. Okay. So this guy is measuring the DNI, the direct normal irradiation. Direct and normal at 90 degrees. Okay. Now, here, the guy will have to stand like that. He's going to hold it like that, okay, to get the direct normal radiation. And then at 6 o'clock, he can't stand on this side of the building. He will have to go and stand on that side of the building, keeping it like that. Okay. Okay, so the DNI, well, this is called the GHI. Okay, so what you're measuring on that surface is always the GHI. Okay. GHI, that one there, and the DNI. Okay, GHI and the DNI. Okay, so if we would now draw a curve of the DNI from 6 o'clock until about 1800 hours. What would happen with the DNI? It would be approximately a constant. Okay? Because you always get the same radiation. Okay. While this one, the GHI, is what a surface horizontally to the Earth would absorb. So in the morning, when the sun rises, it is cos of 90 degrees, it's almost zero. Then cos of 89 degrees, which is a small value. And the result is that it will do something like that. Okay. So at 12 o'clock, the two values would be the same. You agree? Okay. Okay. And then the last value that we are interested in is the one which is the diffuse one. The diffuse component, which is this component in red on the graph. Or at least if you can go to the graph again. So what do you see there? The diffuse radiation. Okay. So the GHI is equal to the DHI plus the DNI. Okay. The DHI plus the DNI. Okay, so the DNI is the direct normal radiation, and this one is the diffuse horizontal. The diffuse horizontal. Okay. Okay, so if we look at what happens now on the roof of Engineering 1, then you will see the two lines up there very close to each other. And here we will see the diffuse radiation. And you will see it is approximately 100 watts per square meters. Okay. Now the roof of Engineering 1 is quite high. Okay. So the reflection from other buildings is almost negligible. So the diffuse radiation is everything from the clouds in the atmosphere, approximately 100 watts per square meters. The DNI, okay, is the green line. Okay, so that is the direct one. Okay. And the GHI is then the sum of the two. So that is the one that you would like to use to design with. Okay. And you will see that the peak was approximately 900 watts per square meters. Okay, and it's not fully summer yet. Okay, so we are still moving, so that we are still moving closer to the sun, so that we can get a better angle from the sun. Okay. Any questions?
So if somebody say wants to sell you a solar panel or a pump and that whole setup, and it says no, it produces like 1.3 kilowatt, and it's like 1 square meter, you can tell it no.
No, it can't be. Yeah, it can't be. Yeah, this already tells you. This is sort of, you know, what can be done if you've got somebody out of the atmosphere, 1,300. Okay. The only exception that you can get is that, I mean, if, for example, and it's maybe a little bit of a ridiculous type of application, is if you've got a tower here and you've got something else here and you reflect some of the sun to that surface. So if you've got something else reflecting, surely that can add to it. But in terms of our normal design environments with houses and buildings, where it changes from one application, from one building to another building quite a lot, okay, it's very difficult to quantify the effect of trees and other buildings, but it's not significant. It's never significant. But you can actually measure it. I've got a meter. You can just go wherever you want to and you can go and measure what the radiation is. Okay. All the radiation together, you can measure what it is. You wanted to ask a question?
I'm just wondering about the semester test.
Okay. The semester test, let me just finish the video, then we're going to speak about the semester test. Okay. Right. Let me see. There's still a few minutes. Not finished yet. Okay. Another concept that we have to look at is the temperature of the atmosphere. So if we look at the Earth, and this is the sun, and we would start making things a little bit simpler now and say, well, that is the radiation from the sun, which is G solar. Some of it is reflected, we know, and then we also have the atmosphere here. And it also has radiation, as I've measured, as I've shown to you. Typically, here close to us, 100 watts per square meters. Part of it would be reflected. What we're going to do is to make things a little bit, to give things a little bit more order, we're going to call that the G of the sky. Okay, G of the sky. And what is being absorbed here is alpha multiplied by G solar. And this is alpha multiplied by G sky. Okay. And this sum is what is being absorbed by the Earth. This is what the Earth would absorb. Okay. Obviously not the part that is reflected, but these two components together, the absorptivity multiplied by G solar plus the observativity of the atmosphere multiplied by G sky. Now, this is very important, and I'm see we're running out of time, so I will discuss that with you in the next lecture. Okay. Thanks, Marlies.